Hi everybody, welcome back from spring break. This is our first real analysis lecture. And to get started, I'm going to review the statement of a theorem that we covered before we went on spring break. I know we did this particular theorem. I'm not sure how far after this we got. But let's just review what it says. Let C be any real number in the open interval AB, and suppose that f of x and g of x are defined for all x values in this interval, except maybe for x equals c. Maybe f of x and g of x are not defined at this point, but they're defined for all other x values in this interval. Also, suppose that throughout this entire interval, f of x is always less than or equal to g of x for all x values in this interval, except maybe at x equals c. So for all x values in this interval, except maybe x equals c, f of x is less than or equal to g of x. And suppose finally that the limits as x approaches c of f of x and g of x exist. Then under these conditions, the limit as x approaches c of f of x is going to be less than or equal to the limit as x approaches c of g of x. And that makes sense. Intuitively, it's obvious. If f of x is less than or equal to g of x throughout the entire interval AB, except maybe at this one point, well, then the limit of f of x should be less than or equal to the limit of g of x throughout the entire interval. And that's what the theorem is saying. Now, why do we say that maybe f of x and g of x are defined for all x values here, except maybe at x equals c? Because it is possible for the limit of a function to be defined as x approaches a value at which the function does not exist. For example, in Cal 1, oftentimes we had, let's see, this will be a good one. In Cal 1, we had limits like this, where if we plug in the value that x approaches, let's see, we get 1 minus 1 is 0 on top, 4 minus 4 is 0 on the bottom. Yet if we plug in the number that x approaches, the function f of x isn't defined. But that didn't mean that the limit didn't exist. We found out in Cal 1 that the thing to do is just to multiply top and bottom by the radical conjugate . And then what would we get if we did that? Let's see. We get the first thing squared minus the second thing squared. And on the bottom, well, let's see. We just write these as distinct factors because I've done this enough to know that this is the factor that's going to cancel out. As a matter of fact, x minus 3 minus 1, ooh, that is x equals, I'm sorry, that is x minus 4. So, we have x minus 4 on top and x minus 4 on the bottom times some other junk. And we go, yay, we can cancel out the troublemakers. And we found out that that left us with what, limit over garbage. And when we plugged in, we got 1 over 1 plus 1, which equals 1/2. So the limit of this function turned out to exist. It was equal to 1/2. But this function was not defined at the value that x was approaching. And this is exactly the kind of thing that may be happening in our theorem. We're saying that f of x and g of x are defined for all x values in this interval, except maybe x equals c, the value that x is going to be approaching when we compute our limits. So that's why we had that stipulation in the statement of the theorem. Take a minute or two to write it down, look at the statement of the theorem, get comfortable with it, and then we will proceed to something that we may have done before spring break, but I'm not completely sure. Okay, time's up. If you want to see the board anymore, you're going to hit the pause button. Ooh, and I did not want to do that. Shame on me. I just want to make sure that I don't start writing out of the range of the video. There we go. Okay, next. The sandwich theorem. Let me try that again. There we go. Okay, so now we have three functions that are defined for all values of x in this interval, except perhaps at x equals c. And suppose that for all values of x in this interval, except maybe x equals c, that f of x is less than or equal to g of x is less than or equal to h of x. And one more thing. Suppose that f of x and f of x and h of x have the same limit as x approaches c. As x approaches c, f of x approaches L. As x approaches c, h of x approaches L. So f of x and h of x have the same limit as x approaches c. Well, what are we supposed to conclude? We already know that for all values of x in this interval, except maybe x equals c, g of x is sandwiched in between f of x and h of x. So why wouldn't the limit of g of x also be sandwiched in between the limit of f of x and the limit of h of x? It is. And since f of x and h of x have the same limit, L, that's going to be what the limit of g of x is. Intuitively, we'd be shocked if this didn't turn out to be the case. Now, take a look at the statement of the theorem. Write it down. Because in order to prove this, I'm going to have to erase the statement of the theorem. The proof isn't very long, but we don't have much blackboard to work with. So take a look at that, read it over again, get comfortable with it, and then we're going to prove it. Okay, if you want to look at it some more, you're going to have to hit the pause button. The previous theorem said that if f of x was less than or equal to g of x, for all x values in the interval except maybe x equals c, then the limit as x approaches c of f of x is going to be less than or equal to the limit as x approaches c of g of x. And we'll note also that by our hypothesis, that thing equals L. Now we can apply the previous theorem to g of x and h of x too. The previous theorem says that if g of x is less than or equal to h of x for all x values in the interval, except maybe x equals c, then the limit of g of x as x approaches c is going to be less than or equal to the limit of h of x as x approaches c. And by our hypothesis, the limit of h of x is equal to L. Well, guess what? When we put these two things together, this is what we have. The limit of g of x is greater than or equal to L and less than or equal to L. Well, how is that possible? There's only one way that this can happen. It has to be that the limit as x approaches c of g of x equals L. Another way that we could put that, the limit of g of x has to be equal to the limits of f of x and h of x. So limit of g of x has to be equal to these two limits. Or if we have the limit of g of x sandwiched between the same real number, the limit of g of x has to be equal to that real number. Take a look at it. By the way, I hope you're taking notes and writing this down and thinking about it. You should be. Write it down, think about what we're talking about, just as if we were in class in person. Now, before we do anything more, I'm going to have to talk a little bit about radian measure. XB, yeah, the measure. So x is the radian measure of an angle whose vertex is at the origin. And we'll consider a circle of radius r. With center at the origin. And we'll let S be the length of the arc that is defined the intersection of the circumference of the circle and the initial Okay, I think we have all the main characters here. I haven't said anything about the plot, but we have all of the main characters. And I guess what I should do now is draw a picture. You'll have to forgive my circle. Somebody dropped it on its head when it was a baby. Okay, there's my circle of radius r, so this point will be r0. This point will be the origin 0, 0. And this point will be 0r. And let's see, the initial side of my angle will be the x-axis for convenience sake. And this will be the terminal side. And x is the measure in radians of that angle. So I have most of the main characters up there. I think I am still lacking one main character. And that's the arc length. This is the portion of the circumference that's defined by the intersection of the initial side of the angle, the terminal side of the angle, and the circumference of the circle. Okay. Now I have to add to this definition. But in order to do that, I'm going to have to erase some of the board. Sorry about that. But this is the best we can do, I guess, right now. The radian measure is the length of the arc over the radius. That's what it is. Now I guess the question comes up, well, what happens if we have a circle with a different radius? It doesn't matter. For a given angle of fixed measure, the ratio of the arc length and the radius is always a constant. And that constant is the radian measure of the angle. Okay, we've defined the radian measure of the angle. Now I need to mention one other thing. Special case. So suppose r equals 1. We're talking about the unit circle. in the case where we're using the unit circle, then it turns out that numerically, the radian measure of the angle is equal to the arc length. Numerically, they are equal. And so most of the time when we're doing theoretical things about trig functions, we choose to use the unit circle just for convenience. Things work out nice. And so in the theorem that we're about to prove, we're going to be using the unit circle. And since we'll be using the unit circle, it's going to turn out that the radian measure of our angle is going to be exactly the same as the arc length defined by the intersection of the circumference of the circle with the terminal and initial sides of the angle. I'll give you a minute or two to look at that. Well, I'll give you a second or two to look at that. And then I will erase and start our theorem. The limit as x goes to 0 of sine of x is 0, and x is measured in radians. By the way, in calculus and analysis, whenever we're working with trigonometric functions and angles, we're always working with radian measure. It's never anything else. Certainly not degrees. When we do calculus and analysis with trigonometric functions and angles, the measurement of angles is always in radians. Okay. For the sake of convenience, we're going to assume that